Our third lesson in Chapter 8 is focused on what happens if I don't have all of my data. In other words, I don't have the XY table. All I have instead is summary statistics. And so we can still calculate the line of best fit, or your regression line, whatever word you prefer to use there, but we can find it with just summary statistics. And so this lesson today is all about formulas. And so our first thing we have to calculate is our slope. And so the formula for slope, which we use B1 as our notation, is R, which is your correlation, times the standard deviation, S, for your Y values, divided by the standard deviation, S, for your X values. So correlation times S standard times the Y standard deviation divided by the X standard deviation. Once you have your slope, then you're ready to find your y-intercept. The y-intercept is b sub 0. To find that, we take y bar, which is our y mean, minus b sub 1 that we just found, times x bar, which is our x mean. And then, once you have both b sub 1 and b sub 0, you're ready to write your model. And our model is always in this order: y hat equals b sub 0 plus b sub 1 x. And so we're going to go through 3 examples. The first one is just going to be, I give you the 6 pieces, practice putting them in the right spots. So this one, I'm telling you straight off the bat, x bar is 65, s sub x is 4, y bar is 150, s sub y is 30, and r is 0.62. And so this is just to practice the formulas. So the first formula that we have to find is the slope b sub 1. And again, that's the formula r times s sub y divided by s sub x. So let's put all the right numbers in the right spots. So r is 0.62 times s sub y is 30 divided by s sub x is 4. Type that in your calculator exactly how you see it. 0.62 times 30 divided by 4, and I get 4.65. And so that's how you find b sub 1. Now the b sub 0 formula, I'm going to recopy that as well. Y bar minus b sub 1 x bar. So y bar was 150 minus, my pen's being, there we go. B1 was 4.65 times x bar, which is 65. Again, type that in exactly how you see it, and I get negative 152.25. And so now you're ready to write your model. Our models always start with y hat, and it's always b sub 0 first, so negative 152.25, plus, then it's b sub 1, 4.65, times x. And so that's how you find your model if all you have is standard deviations and means. Now this was very straightforward. Now we're going to put it into the context of a word problem. So the scatter plot shows the total mortgages in the United States in millions of dollars versus the interest rate at various times over the past 26 years. The correlation is R equals negative 0.84. The mean mortgage amount is 151.9 million, and the mean interest rate is 8.88%. The standard deviations are 23.86 million for mortgage amounts and 2.58% for interest rates. So the first question asks, is a regression model appropriate for predicting mortgage amounts from interest rates? And so there's 2 things that you always have to check. The first thing you have to check, is the data quantitative? And then the other thing you have to check is your graph look somewhat linear? And so if you answer yes to both of those, then you're good. So is this data quantitative? Well, interest rates are in percentages and mortgage rates are in dollars. Those are both measurable. So yes, it is quantitative. Is our graph linear? Other than maybe this little dot way up here, it looks like it kind of all fits in that linear pattern. So we're going to say yes to linear as well. So yes, a regression model is appropriate because it's quantitative and linear. So now we need to go back, and before we go, I'm going to make life easy. Before we skip to the next slide, I want to label some things. So we know, just by looking at what we've done so far, that interest rates are X and mortgages are Y. I want to label all of my data values with the important numbers that I need. So we know the correlation that was given to us. That's right here, and it's labeled R already. But it says the mean mortgage amount is 151.9. That is a Y measurement, and it's Y bar. The mean interest rate is an X value, and it's X bar. The standard deviations, the mortgage one is S sub Y, and the interest rate one is S sub X, because we will need all of those when we flip the page. So now, what is the equation that predicts the mortgage amounts from the interest rates? And so that's where we find our two pieces. We find B sub 1, which we find by taking R times S sub Y divided by S sub X. R we already had labeled as negative 0.84 times, if you go back and look what we put S sub Y next to, that was 23.86 divided by, and S sub X we put next to 2.58. Those 8s don't look very good. Whoa, I'm really having issues here. Okay, so if you type all of that in the calculator, I got negative 7.77. By the way, if things don't come out perfect, if you get long decimals, just use 2 decimal places and you're good. So then we have to find B sub 0, and that formula again was Y bar minus B sub 1 X bar. So Y bar was what we put next to 151.9 minus, we just found B sub 1 to be negative 7.77. Notice there's a double negative there. Times X bar we put next to 8.88. And if you put all that in the calculator, I get 220.90. And so my model, Y hat, would be 220.90 minus 7.77x. So nothing tough there, but you had to label which numbers were what before you could use them. What would you predict the mortgage amount would be if the interest rates climbed to 20%? So this is a prediction. So I'm plugged 20% in for X. So Y hat equals 220.90 minus 7.77 times 20. Put that in your calculator, and I end up with 65.6, or nope, 65.5, and this is in millions of dollars. So I'm going to write million, and I'm going to put a dollar sign. Do we have any reservations about our prediction? This was the are we confident question. So the big thing is 20 within our range of data. And if you go back and you look at your graph, the interest rates went from 6 to 16. So that is off of our graph. So what we can say is, do we have any reservations? Yes, because 20% is off the graph and outside of our range. And so that's how you use one that's in word problem form. It's just a matter of labeling what's what. Let's look at another one in word problem form. For an online clothing retailer, the scatter plot of total yearly purchases by income is shown below. The correlation between total yearly purchases and income is 0.722. The summary statistics for the two variables are, and we organize everything into a nice table. So again, it's asking what is the linear regression equation? So again, income is X's, yearly purchases is Y. So I'm going to label that. So income is my X's, yearly purchases is my Y's. The means and the standard deviations are labeled, and this guy up here, that's my correlation, so that's the letter R. So to find my model, B sub 1, we're going to take R times S sub Y divided by S sub X. So R is 0.722 times standard deviation, so we're using this column. The Y is the 253.62 divided by the X is 16,952.50. Now when you put all of that in the graphing calculator, you should hopefully get what I got, which is 0.01. So now let's find our B sub 0. Again, that's Y bar minus B sub 1 times X bar. And so Y bar, now we're on to the mean column, which is this one. The Y is 572.52 minus our B sub 0, or sorry, our B sub 1 is 0.01 times our X bar is 50,343.40. So go ahead and type all of that in the calculator, and hopefully you get 69.09 like I did. And so our model is Y hat equals 69.09 and then plus 0.01x. And so let's move to the next page. So do the assumptions and conditions for regression appear to be met? Again, those assumptions were, is our data quantitative and is our graph linear? So our data was income in thousands of dollars and purchases also in dollars. And so they were both in dollars. And so yes, that's definitely quantitative. And if you look at if you go back and look at the graph, it's a very wide band, but it's definitely a linear band. So yes to both of those. So yes, we are good with linear. What is the predicted average total yearly purchases for someone with an income of $20,000 and then someone with an income of $80,000? So those are both prediction questions. So our model was 69.09 plus 0.01, and so I'm going to multiply first by 20,000, and then I'm going to do the same thing but I'm going to put in 80,000 in the parentheses. So go ahead and pick up your calculators, type in the first one with 20,000, and hopefully you get the exact answer I get of 269.09, and then go back and do the exact same thing for 80,000, and I got 869.09. And so those are your two predictions. what percent of variability in total yearly purchases is accounted for by this model? When they ask for percent of variability, they're wanting R squared. Well, the only way that we usually find R squared is by using the graphing calculator. But R squared can also be found by taking R and squaring it. And R is correlation. So when they ask for this, you can take your correlation and square it. So our correlation was 0.722. So I'm going to square that. And my calculator spits out 0.52. And then I'm going to multiply that by 100 because I need it in percent form. So 52% of the total yearly purchases, 52% of the variability is accounted for by this model. So this is an example where there was outside reasons that people either didn't purchase a lot or did purchase a lot. Maybe they were saving up for something bigger. Maybe they had other bills to pay that year. So there are definitely outside reasons that people may not spend a lot at a shopping for like personal shopping when there's other things that affect where their money goes. So that's why that percentage was low. And so that's the end of this lesson, and we'll finish up chapter 8 next time.